I shall start my lecture with a statement of some known conjectures about Klosterman sums and elliptic curves. What do we mean by Klosterman sums? We take a finite field of order P, its additive character, that is exponent P of x equals and maybe some integer term here. And then we take the sum of the following form. First studied by Klosterman and known already to Poincaré. The famous statement about this sum is that it doesn't exceed 2 square root of p. And so by weight estimate, we know that this ratio lies in interval -1, 1 on a real line. And we may be interested in distribution of these numbers in the interval. The conjecture is as follows. For any subinterval, we consider the number of p, of prime p, less or equals x, such that this ratio lies in this interval. We divide that number of such p, we divide that by number of all prime numbers less or equal x, and consider the limit at infinity. And conjecture is that this limit equals to such integral. That is, we can treat that as probability measure defined on intervals, subintervals of this interval. And this measure and this density of the measure are known as Sato-Tate measure and Sato-Tate density. It is not proved. It's unknown how to prove this statement, but it's known already from Serre. We can restate that in trigonometric form, since this number is less or equal to this one, we can define the angles theta such that we have such equality, and our previous statement is the same as this one. One more conjecture deals with elliptic curves over prime field 0 pt. If EP is such an elliptic curve, then the number of points on this curve equals p plus 1 plus something, some remainder term, which is less or equal to square root of p. And again, we may consider the ratio Rp divided to square root of p, and to consider the distribution of these ratios in intervals within interval -1, 1. We take number of such p divided by the number of all prime p less of x, and it is expected that the limit equals the right-hand side here. So it is the same thing as in the previous conjecture. This conjecture has been proved in some particular cases. for some, not for all elliptic curves. I would like to look at possible generalization of these conjectures relative to so-called polynomial character sums. What is SP? We take two polynomials over integers, and additive character of our field, prime field, finite field, and some multiplicative character of the same field. We take the product and the summation in some with sum over all elements of our prime field. That are so-called mixed polynomial character sums. We may notice that the Clustermann sum also can be written in such form. Namely, we can rewrite the definition in such as Fourier expansion of Clustermann sums, and we have here some polynomial and character. Under very general assumptions about polynomials and characters, we can attach to our sum the so-called ordinal function, which occurs to be polynomial. And if we write a polynomial as a product like that, so that are inverse roots of polynomial, then the character sum equals to the sum of the roots. In the case of Clustermann sums, we have two terms in this sum. In these formulas, we have the notations are as follows. We need and it should be degree of polynomial b, and as to a, its reduction modulo p should be polynomial of degree m. Radical of a of its reduction is polynomial of degree m. And by these two numbers, we determine a number of roots. Then, for the zeros of an ordinal function, we have the equality like that. That is a finite field analog of the Riemann hypothesis for zeta function. It was proved in 1948 by Andre Weil. So, if, from this expression and this one, we obtain an upper estimate for our character sums. Now, okay, let us return to the definition, to this definition. If we're interested to consider the conjecture like that, we should choose character x pi for each pi in some reasonable and fruitful way. Say, if we deal with Clustermann sums, we have quadratic character in here, and there is exactly one quadratic character for each field. If we interested in sums with characters of higher order, then the problem is that there are many characters of the same order for given field, and so it is a problem of choice of them. There is no natural way to define characters in conjectures like Sutherland conjecture. And my idea to give some suggestion for which allows us to generalize the stated above conjectures. We take characters, additive characters in here, like that. That is not problem. That is a uniform definition, which is valid for all P. And then we do as follows. We take some integer L and some root W of degree H from unity. Then we consider not all the primes, but we define some set of prime P, which is defined as follows. The prime P is in omega L if it conjugates one modulo H and satisfies the condition for the field ZP over PZ. There exists unique character of order H which has value W at the point L. In this definition, the first condition, just necessary and sufficient conditions for existence of characters P of order H. As to the second condition, I would like to say that in some particular cases, when H, if H is prime, when this just means that L is not H degree in this field. And now, if we fix our parameters into L, W, and H, we said, and the character described in here, the unique character satisfied with conditions. Then let us write a number of full prime in our set, which less or equal x. And if SP is measured as in Weil estimates, then we can consider the following ratio, SP over square root of P, and consider number of primes in our set omega L, which lies in some measurable subset of a circle of radius R with center of 0. And we may look at the limit at x tends to infinity, and that should be some measure with some density, which should be determined. It may be something like square root of something like in the conjecture. No, maybe in the entirely maybe different functions. So my suggestion is that this is quite adequate and fruitful generalization for conjectures above for Clustermann sums for some elliptic curves. Also, we may some remarks. If we deal with character sums which are real for HP, then we may replace circle by intervals, and also we can consider similar questions concerning absolute values of our sum or some trigonometric form. Maybe I should explain better. Say, I would like to explain the reason to introduce such type omega sets omega L. Really, there is no L in definition of our character sums. That is some auxiliary parameter. So assume a problem or questions like that, which you have, say, exponent, and you would like to define inverse function logarithm. It's not impossible to do immediately because for each complex number, see, there are many points such that exponent of them equals this point. What we do, if we're interested in inverse function, we first introduce continuity condition. And then we introduce one more condition. We take complex plane and we remove some curve which starts at 0. And so we restrict the definition of an inverse function. Just the same I do here in definition of omega L. Instead of consideration of all prime P, I restrict the set. By this condition, it's just similar to this one. And when the condition, but unique of this one, and adjust, we need similar to cutting of some curve. We expect the conjecture for the function in here, C in here. We expect formulas like that. In the case when ordinal function attached to our character sums has just two roots. But if it has more than two roots, then the functions expected should be more complicated. And I would like to point out that we can study the questions like that numerically by means of systems like Maple, because we have some necessary functions like prime roots, say prime roots in Maple, in number theory, there is such time command in number theory part of Maple. And we think we can evaluate all multiplicative characters and to study numerically the problems like that. Okay, maybe that's all. Thank you.